Hello, welcome back. So in this part, we will see how do we check our beam for the deflection. So about this deflection, I have explained in the steps that we follow IS code recommendation, and as per IS code of this close point A and point B, the ratio L by D, the ratio L by D should be less than 20 times of modification factor. Well, how this 20 and modification factor, this equation I have formed, I have already explained this in the steps, so you can check that if it is not clear to you. So all values are given here. L value we already know, D also known. We already, the unknown value is modification factor. How do we find out this modification factor? That we will see. So first of all, we have to refer figure number 4, the same figure that I have shown you in the IS code also. And as from the figure, we have to find out this Fs value. This Fs value is 0.58 into Fy into AST required upon AST provided. I will show you the same formula in the IS code also. I will show you that now. So there you can see this graph we will use to find out this modification factor. This modification factor depends on two parameters. First, percentage of tension reinforcement that we have already calculated, which is 0.43%, and the next parameter is Fs curve. So this Fs value is to be find out. So Fs value can be find out using this formula. So again, I am showing you the slide, because there I have calculated the Fs value. So Fs formula is given in the IS code, which is 0.58 times of Fy into AST required upon AST provided. So Fy is 415, AST required is 668, and AST provided is 804. This again we have already calculated. So calculating this value, Fs value comes out as 200.19. Now we have to find out modification factor from the graph. How do we find out from the graph? That we will see now. So in the graph now, see our percentage of steel. Our percentage of steel is 0.43%. Okay, and Fs value is 200. Okay, so now you can see here this curve is for 290, and this curve is for 240, and this curve is for 190. So you can see our curve for 200, it will be just below the 290 curve. So just we have to imagine, we have to visualize our curve. It will be running like this, something like this. It will be running like this. It will be running like this. And also the percentage of steel is 0.43, which is near to this 0.4 value. So what we have to do is we have to visualize now the value of Fs. Where this line, if I try here, this will go there, and it will bisect this curve near 1.5 value. So this value will bisect here, and corresponding to this, the value of modification factor can be read as 1.5. So this is how we find out the modification factor. First, we will check the Fs curve. Just we will imagine where that curve will lie. So this curve is 190 for 190, and our Fs value is 200. So curve for 200 will be just below the 190 value. And if we go this like this, and if we extend this line, so where this curve will cut, and corresponding to that we will read the modification factor value. So this is how we read the modification factor value. So from the graph we can find out MF1 as 1.5. So now we will put this value in the equation to satisfy the condition of the deflection. So now here Fs value we have already calculated, and percentage at midspan, again please correct this is actually 0.43. We have calculated 0.43% has here. So for 0.43, we have calculated now the MF from figure 4. So MF1 value comes out as 1.5. So now we will put this value in this equation, and now we have all the value we can easily calculate here. So L is the effective span, which is 5300, and 511 will be the effective depth, and it should be less than 20 times of 1.5, which means it is actually satisfying. So this ratio is 10.3, which is less than this, the product of this. So if this condition is satisfying, we can easily say that our beam is safe in deflection. By chance, if it is not satisfying, in that case we have to increase the d value. So we can say that beam is safe in deflection in this case. Now we will check our beam for the shear consideration also, and I have already explained how do we find out uh, various parameters in the shear force check. So first we have to find out V value. V is the W L by 2. So W we have already the value, which is 20.08, and clear span is 5100. So putting the value, we can find out V value as 51.204. This we have calculated earlier. The value, this value is already given in the question. And how do we find out this, I have already explained in one of the part, so please refer to that if it is not clear to you. Then this V value in it is we can convert this value in the Newton also. So now we can easily find out the value of tau V, and tau V is V upon BD. This tau V is actually V upon B into D. So V value is there and B and D value is there. So we have to make sure that B and D value will be in mm and V value will be in the Newton. So that is why I have converted this into Newton, so that we can get this stress value in Newton per mm square. So the value of tau V is 0.27 Newton per mm square. So here you can see the value of tau V is less than tau C max, and tau C max we can find out this value from table 24 of IS code, and for M20 grade of concrete it is 1.8. So you can clearly see that the value of tau V is less than tau C max, which is 1.8 Newton per mm square. So which means the beam is safe for diagonal compression criteria. So diagonal compression is taken care of by this phenomena, which means tau V is less than tau C max. So it is safe in diagonal compression. But now we have to check whether our beam is safe in diagonal tension also, because diagonal compression and diagonal tension both occurs because of the shear force action. So I have already explained this. So I hope it is clear to you. So now we can say that because tau V is less than tau C max, so we can say that beam dimensions are okay from the shear consideration. Now coming to the now we have to find out another parameter, which is permissible shear stress in concrete without shear reinforcement, which is tau C. Now to calculate the value of tau C, we have to find out the I mean, you can see here that this will be our beam, and till now what we have done is we have found the depth and length of the beam is already given, and also the tension reinforcement is also we have found out this value. So these bars are 4 bars of 16 dia, you know. So we have already find out this value. So now we have to see how much bars we will bend up. So as I said, bent up bars can be number of bent up bars that we can bend up will be total number of bars minus 2. So at support, at least 2 bars should be there, which means we will say that 2 bars will be bent up like this. 2 bars will be bent up like this. So now if I cut cross section here, 4 bars will be there. There will be 4 bars. If I cut cross section here, then 2 bars will be here and 2 bars are here. Okay, so this is how we take. So to find out the value of tau c, it is very important to check how much reinforcement is at the support on the tension side. So now you can see 2 bars are bent up. So only bars which are left here on the support are these 2 bars at the support. So now to calculate the value of tau c, we will refer to table number 23 and I will show you that table. So there you can see this is the table that we have to see to find out the value of tau c. So to find out the value of tau c, we need to find out this percentage. So this percentage is actually, I will write here, percentage of tension steel at support. So as 2 bars are bent up, so we will say that percentage of steel we will calculate for the 2 bars. So it will be 100 multiplied by this AS. AS is the area of cross section for the reinforcement at support. So at support only 2 bars are there now. So 2 multiplied by pi d square by 4 upon में D will be 370 multiplied by D. Now D value is 511. So now by solving this, we can easily find out the percentage. I mean, we can easily find out the value of tau c. So how much value is there? We will see that in the slide. Sorry. So as you can see, to find out the value of tau c, first we have to assume how much bars are bent up. So I have already cleared that we are assuming that 2 bars are bent up at support, and which means number of bars at supports are 2. So AST at support is 2 into pi d square by 4, and percentage, now we are calculating the percentage, which is 401, and after calculation we find the percentage of steel, tensile steel at support is 0.21%. Okay, so now we will look for tau c again from the table. So again I will show you the same table. So there you can see for percentage of steel in our case is now 0.21%. So you can see for percentage of steel 0.15 or less than that, the value of tau c is given here. For percentage of steel 0.25, it is given here. So our value of percentage lies between 0.15 and 0.25, which means we have to do interpolation, and also we are using M20 grade of concrete. So now for 0.15 M20 value, I mean tau c value for M20 grade is 0.18, and for 0.25 it is 0.22, which means we have to do interpolation. So tau c value for 0.21%, we can easily find out this as 0.18 plus difference between these two, which is 0.22 minus 0.818 upon, now difference between these two, which is 0.25 minus 0.15, and multiplied by 0.21 minus 0.18. So this is how we do the interpolation in this case. So 0.18 is the corresponding value of 0.15, and as you can see it is increasing, so that is why I have done this, I have added it. Okay, so this is how we do the interpolation. So I hope it is clear to you, because we have already done this earlier also. So using interpolation, we can easily find out tau c value as 0.20. So now you can see, now we have tau v value, tau c max value, and tau c value. Now we have to check whether we are required shear reinforcement or not, because diagonal compression is take care of, but still we have to take care of diagonal tension also. So as here we can see that tau c value is less than tau v, because tau v value was 0.27 and tau c value is 0.20, which means it is not safe in shear. So which means we have to provide shear reinforcement. Okay, so that is our this step. So in the step 11 we will design shear reinforcement. Okay, so this we will design in the next part. Thank you.